Good morning, everyone. Bonjour, guten morgen, bon dia, buenos dias. From the Netherlands, in the city called Enschede, we are welcoming you to this tech talk or conference, as you wish. Outside it's cold and white, inside it's green, you don't see it. But from here I will host this tech talk together with our partners. Probably you have seen already the agenda, the lineup. I will shortly go through it. Basically, we go from the fields, the wine fields of Italy. We go to the GNSS Mecca in Belgium. Then we will have a short intermezzo here in the Netherlands again. Then we go to Germany, Bayern, where more the beer is more present. Then we go to the hills and tunnels of Switzerland. And we will end up again in the Netherlands with Nobleo. Our first speaker for today is Nicolo from FieldRobotics. They are based in Bologna. Probably you know the place, a great city near all the wine fields. And Nicolo will tell you more about their robotic vehicle that we also saw 2 weeks ago at the Agritechnica. Probably you were there also. They were the star of the Hall 15, where we were also present, and they showed already their vehicle which is ready to be deployed in the fields. So, Nicolo, I would like to give you the word, and later on I will speak to you again.
I'm Niccolò Omodei from Italy. I'm an automation engineer at FieldRobotics. And first of all, I would like to thank you, all the Movella staff, for this organization, and for letting me show all the FieldRobotics concept today. And FieldRobotics is a startup established 1 year ago in Bologna, starting from a university project here at the University of Bologna for sure. 4 professors decided to bring out this project from the university and bring the project to the market. So nowadays we are 10-15 people with different several background, most of us from automation engineer, but we have for sure, of course, also some mechanical engineer and some computer science engineer in our team. So FieldRobotics has the main core expertise in autonomous navigation system in GPS denied scenarios. So our algorithm, our software can be applied to terrestrial vehicle, but also to aerial vehicle. And so with this kind of system, we are capable to navigate also where the GPS is not present. We have, of course, AI solutions in order to perform image segmentation and to perform also object recognition. So will our vehicle autonomously move in the environment, we are capable to collect data and perform what is called data harvesting, and then all the data will be processed and in order to extract some useful informations. So FieldRobotics has 2 main divisions. The first one is the search and rescue division, which is focused more on aerial vehicle in order to perform, of course, search and rescue in very harsh environments and perform also land and sea defense. The second division is about agriculture. Here we developed a multi-purpose platform in order to perform every kind of operation needed inside orchard and vineyards. So today my aim is to show you the agriculture division inside FieldRobotics. Our mission is to develop and commercialize a platform which is fully autonomous and fully electric, and has a sort of plug-and-play array that allows the platform to perform every kind of operation. So the vision here is quite different from the standard, because we would like to redefine the tractor concept in order to don't have anymore the traditional tractor on the field. So the main concept that guided us during the whole development is that we would like to have a powered implement instead of a tractor pulling implement. And with this concept in mind, we can reach a compact and integrated design with a very, very lightweight structure, which allow us to have a very, very slow soil compaction in every kind of weather. The other main concept and main feature is the adaptability and flexibility of the platform. You can imagine that once you have an autonomous platform working and autonomously move in the field, you can then design a sort of plug-and-play array of implements. We very believe in a new generation of tools, because nowadays we are used to see very power demanding implement with very big structure, but maybe all that weight is not necessary in order to perform the operation. So what we are doing is try to redesign the standard implement in order to adapt them to our platform and have, of course, a very low power demand. Then another feature is what I like to call the power bank in the field, because once you have the platform that moves autonomously and you have battery on that platform, you can imagine that you can attach every kind of things that you want and charge every kind of implement that you want. I was thinking about maybe scissors in order to perform pruning, tree pruning. Here another big concept is the solution in which we have in mind, and that is that a larger number of small tractors is better than a small number of large tractor. We are used to see very, very big tractors in the field with a lot of power that maybe is not needed. Of course, we have some examples nowadays inside warehouse where we have all these AGV moving autonomously and working as a fleet. So we would like to bring out from the warehouse the fleet concept and have more small tractors, a large number of small tractors inside the field, which are capable to communicate and perform maybe some operation together and collaborate together. So here in the image, you can see our first prototype called Daedalus, with the old feature that I told you before. So we have very small and lightweight structure, which allow us to have stability and robustness. And of course, this is a platform capable to perform autonomous navigation and is full electric. With the track design, we have a very high stability. On the image there, you can see some tests that we perform inside our lab. Comes out that we are capable to navigate up to 50 degrees of slope. And so we are capable to navigate also in those fields where there is very, very high steep and with a high slope. Then we developed a second prototype with the same concept of the first one, but you can see in the image with a very renewed design. And this is more like an industrial product. On this platform, we have more power because we have two 5 kilowatt motors for the traction, and then we have a 10 kilowatt motor just for the PTO. For those of you who is more familiar with agriculture concept, in the image there on back of the platform, you can see the 3-point hitch with the carbon shaft, which is the universal attachment method. And so with this second prototype, the big feature is that we are compatible with every kind of traditional tool actually on the market. So let's go more in detail about our autonomous navigation. This is more technical part, but I try to take it simple. I would like to, first of all, highlight that all the hardware part, but also the software part has been developed inside FieldRobotics. And we try to maintain a sort of modularity scheme during the developing. In this scheme, every single software component performs a specific function in order to control a submodule or add new functionality to the vehicle. In the scheme there, in the slide, we can see that there are two ways in order to control the vehicle. We have the teleoperation, which must be intended as remote guidance. And of course, we have autonomous navigation. These two subsystems feed the high-level controller, which is responsible to generate trajectories that can be used from the low-level controller in order to move the vehicle. And so the low-level controller takes the informations coming from the high level and from the I/O, from the sensors, and control the actuators. So we have a sort of bidirectional communication between the low level and the high level controller. This is more or less the idea that there is under our autonomous navigation systems. And here we have a more specialized scheme, which is the scheme in order to show you what has been implemented inside our algorithms. We can start analyzing it by seeing the orange part. The orange rectangles are the low-level part, which are intended in order and used in order to take the telemetry in the upside left-hand side, and in order to send commands to motors. Then we have the light blue boxes, which are the sensors that we use. We have, of course, an IMU. We have a GPS RTK receiver, and we have a LiDAR, which is our laser scanner. These sensors give us some raw data that must be processed in order to extract the features that we need in order to perform the navigations. And so these data are passed to the gray box, sorry. In this gray box, we perform the localization, starting from, of course, the odometry, the IMU, and the GPS. And also, we perform the raw direction estimation. All these data are then passed as input to our controller. We have three main controllers inside our rover, and these controllers are specialized, each one for a specific action. The control, the open field control is specialized for a kind of navigation. Then we have the in-row control and the change row control. The output of all these boxes there is used in order to send information to the motors. Here we have our key feature for the navigation, because I didn't mention it before, but inside rows, we don't use the GPS. We just use the laser scanner. So the LiDAR gives us a point cloud, which is a very raw data, and this point cloud is then analyzed. So we have several steps to perform to achieve a perfect estimation. We start with the very raw data. We feed it with the relative orientation and with the sensor position in order to refer every single point of the point cloud to a reference frame which is on board on the vehicle. And since the vehicle is somehow on the ground, we can refer every single point of the point cloud to the ground, the reference frame. In this way, we have a sort of two-dimension point cloud. And starting from this array of two-dimension points, we can, we know, of course, the rover dimensions, and we can hide all the points that are referred to the rover. And then we have a more clean point cloud. And so once we have this clean point cloud, we can start all our HAUC algorithms. These HAUC algorithms perform a sort of votation. We select the votation on the base of distance filters parameters, I mean distance from the reference frame, and also we select the candidate solution based on geometric constraints that are given by previous solutions. And at the end of this process, we are capable to have the raw lines estimation. So now we have seen a sort of more technical part, but let's see how all these algorithms are used in practice. So we have autonomous navigation, which can be divided into three main areas: the open field navigation, the in-row navigation, and the autonomous turns. Let's start with the open field navigation. This is used in order to reach from maybe the warehouse to in order to reach the field in which we have to perform the operation, and is a sort of waypoint navigation in which the user should set a series of waypoints or a series of roads, and then the platform will following that kind of points. Once we are inside the rows, as I told you before, we don't use anymore the GPS signal, but we use just the LiDAR. This because the GPS signal in some environments, in some condition, cannot be as precise as we need, and so we just have to avoid this problem by using other sensors. And so once we perform the row estimation, we are also capable to recognize the end of the row. So from a user perspective, the configuration is very, very straightforward. We just need three parameters. We need the row width for each row, the first turn direction, because all the following turns will be the opposite. And then we have the number of rows that the rover must process in order to complete the whole operation. So just three parameters in order to perform the whole navigation cycle. Then when we are at the end of the row, we are capable to detect the end line and perform and compute a trajectory in order to go inside the following row. We can do that because we have the estimation of the actual row, and we can determine the position of the center of rotation, which is the pivoting point, and in order to enter in the following line. An additional feature that we have is that we're starting to estimate the next line from the very beginning of the operation. In this way, we are capable to have a very high precision in the next row. Here we can see an image. I like to call it robotic-friendly orchards, because we tested the machine in our experimental field in Bologna. And here in the picture, we have a type of this orchard, which is a planar experimental orchard. Those are apple trees, and they have a sort of two-dimension structure. And so this planar structure, of course, you can imagine that is very, it's quite easy to navigate inside this structure. But of course, we tested the robot also in several orchard architectures and also in vineyards. It has more than 1,000 hours in the field, test field. Here we have a picture of our simulation, because we really believe in simulation, but not just from low level point, but also from the high level, because as you can see, we have a very realistic images, and with this realism, we are capable also to train a neural network and to perform object recognition in simulation that can be used then also in real life. Here, just a quick brief on future developments. On the left side, you can see our low dispersion sprayer. What we did here is starting from a traditional sprayer and adapt it to the rover in order, as I was saying before, in order to have a very low power consumption. On the right side, instead, you can see a tool which, again, starting from a very traditional tool, we electrify it, and it's a tool used in order to perform every kind of inter-row operation. Then here we have some futuristic developments, but of course we have some prototypes on them. On the right side, you can see an image of the rover with a sort of robotic arm mounted on the chassis, which is used in order to perform automatic harvesting, fruit harvesting. And then once you have the robotic arm, which harvests the fruits, you have also to have a logistic platform. And this is the purpose of the left side image, in which you can see that on the rover we have a structure capable to load a fruit bin from the front part, load it on the chassis, and then fill it with the harvested fruits. And once it's completely filled, we can discharge the bin from the back part. So I think that I'm at the end of my presentation. I hope that was as clear as possible. I really invite you to follow FieldRobotics social media. I'm in LinkedIn and YouTube, in order to have some information about new developments. Feel free to send me an email at nicolo.omodei@fieldrobotics.it for any kind of information. Of course, I'm here if there are any kind of question.
Thank you, Nicolo. Very, very interesting. Not only the sunny pictures, which remind me of all the Lambrusco wine and the Sangiovese wine in your area, but also, of course, the technical side, the navigation outdoor, dealing with challenges of GNSS, and also, of course, the branches that are blocking everything. I have a couple of questions here that I will ask you, if you don't mind. So the questions that just came in for Nicolas is, the first one came from Bernhard. So what tools do you already have tested or in actions? So basically Bernhard is talking about the implements or the tillage that you have behind your robot.
I would like to highlight that this is a market-ready platform, and the platform, of course, is market-ready, and we have a sort of an array of implements. The implements that we already tested are the mulcher in order to perform the grass cutting inside rows. We have also ready the interrow tool, which is a sort of disc with blades used to perform the cut grassing between trees. And of course, we have the low dispersion sprayer, which can be used in order to perform every kind of spraying operation inside orchards and vineyards. Those three are the three implements that are already on the market yet.
Okay, thank you very much. Then I have a question from Patrick. How do you deal with drift in your location when driving between the rows? So if there's any drift, how do you deal?
We deal it by using, of course, the laser scanner. I mean, once you can see the environment, you are capable to somehow pass any kind of flag due to GPS signal, and so we don't have any drift during navigation.
Okay. Thank you. And then Sarah has a question. How do you estimate the rows?
So there was a previous slide on that. Yeah. And maybe I can just go back there. Here we go. This is our localization inside rows. As I told before, we use the point cloud in order to perform and start the Hawk algorithm, which is an algorithm used mainly in computer vision in order to define rows starting from images.
Yeah, okay, great, thank you. And do you use a map also for the localization? That's a question from Teresa.
We don't use any kind of map. I mean, this is a key feature in my opinion, because as told before, we don't need to map the fields before, but we are capable to navigate, I mean, in real time without any kind of map.
Okay, thank you very much. Yeah, so it's a really flexible and also low processing needs, very efficient way of navigating through the rows. So everyone, we will move on to the next presenter. We don't want to take time from his presentation. Our next presenter is Gustavo Lopez from Belgium. Probably you know him very well. He's very experienced in the GNSS field. And I'm really happy that also Gustavo is joining us in this conference.
Thanks a lot again for the invitation. And I will talk today about GNSS reliability and resilience in the topic of industrial applications. There have been already some very nice presentations, as you saw already from the morning in the robotics side. But there are also other type of use cases that in Septentrio we get to see. And maybe just to start very quickly here to introduce a bit the topic of today. This is a nice quote actually, which tries to talk about reliability, which is the main topic I want to talk today. When we are talking about reliability, it's not necessarily only about the accuracy side. Degrees of accuracy are only degrees of refinement and magnitude in ways that affects fundamental reliability, which refers more to, let's say, to the truth. When we are talking about true information, really making sure that you are truthful and precise. That's really what matters, especially for different type of autonomous applications. So I'll talk a lot about this type of things, but we all know that we want to have a very good, precise, and reliable system. So high level, my outline of presentation, I'll give you a bit of information about the trends in robotics, what's happening out there, what we get to see as a company in the GNSS side. Then I'll focus on the reliability of GNSS and bring in some elements of multipath, multi-frequency. How can that help you in order to have better performance with the GNSS, especially in difficult environments? Some environmental robustness, which also sometimes is important for this type of automation we get to see in the market. The security side, which is what we call the resilience or GNSS security. Why is that increasing as a question mark for some of the customers that are integrated in autonomous systems? And of course, how can we integrate with Movella? We have some nice views on that as well. Let me quickly explain who Septentrio, for those of you who do not know it, is a company of around 130 employees. We are indeed based in Belgium. Indeed, I'm not Belgian, as Minder said, but I'm based in Belgium with the team where we have the headquarters. We have also an R&D second development center in Finland, lots of clever people also around there, and we have support and sales offices in different places. But in general, what we are trying to do is mainly focus in providing what we call dependable or reliable GNSS, which is accurate, reliable, available, and secure in all the different type of use cases. And we provide, of course, systems that go from the modules all the way to some system boxes there. But anyway, that's the high-level part of Septentrio. Let's try to go to the topic itself and what we get to see in Septentrio as trends, especially from this autonomy side. I mean, everything we know started with the autonomous car that we were all promised to have some autonomous cars driving in the streets by this type of years by now, but we know that there is a delay still in this technology. Yes, there is already some automation happening there and it will keep coming, but what we notice in the meantime is that there is a real explosion of autonomous applications in industrial use cases, in robotics use cases, which is creating a great momentum in the market, awareness of the technology. There is a commoditization actually of this technology, and therefore creating also some interesting business for the different companies implementing autonomous technology there. And we get to see that. I mean, there are different type of use cases where you see already autonomy, all the way from the big machinery. As example, here you can see a Komatsu haul truck. Autonomy was already one of the first places where this happened. Autonomy has been there for several years, but we get to see also already other type of systems in logistics, ag robotics, as we saw this morning, and last mile delivery, drones, etc. And this is really an exciting moment that we get to see. Let's start with the industrial side, so the heavy machinery. What we get to see in the heavy machinery. As you know, there are multiple companies, OEMs, creating these big machineries, and they are trying to move into further automation and autonomy of these vehicles in the market itself. Again, all started with these haul trucks that were already kind of autonomous, and we see those already deployed in mines and things like that. But we get to see new type of vehicles that are trying to integrate autonomy also in their use cases for productivity or for other type of safety elements behind that. That's what we get to see in the industrial use cases. And the interesting part is also how these autonomy levels are increasing over time in that market itself. At the beginning, when we are thinking about the level 0, 1, or 2, these type of companies were focusing mainly on creating already kind of a basic autonomy and a steering type of autonomy, which was bringing productivity, efficiency, right? That was basically what they were trying to reach as a main goal. But at the moment that we are starting to integrate all this full autonomy, then the trends became a bit different. People really want to avoid operational shutdowns. They want to have a very safe system behind it. And therefore, the type of requirements that happen on the GNSS or the inertial systems out there are also changing over time as well. So it's very interesting to see what happens there. Then we have robotics, and this is something also I love. And again, I love seeing the talks as we saw this morning, which is bringing fantastic new use cases in different areas. We heard about agriculture, but there are delivery robots, there is marine robots, mowers which are operating in different environments, such as you can see here, solar panels which are obstructed by some of the GNSS signals, security cleaning, snow cleaning, and many other use cases that we get to see in the market, which is very, very interesting to see how this is evolving. And again, the requirements for precision and reliability are also increasing as well. So this will give you a bit of view of the trends or main demands that we have in the market from the GNSS point of view. People want to have systems which are smaller, not for all type of robotics or not for all type of systems, but even if you have a box type of system, they would like you to have it also in a small form factor. Or if it's a very small robot, then you would even like to have a module behind it. All these type of robots or drones sometimes are working with a lot of electronics, communication. You have a processor behind it, data recording. So all this could also create some interference, unwanted interference also in the system, and you need to be very resilient against also those type of interferences. Working in difficult environments, you might have, of course, as we saw, some of the robots actually are working in environments in the streets where there is not always a good visibility of GNSS signals, or even just think about an agricultural robot that is also working next to trees or next to an environment where there is a lot of leaves and therefore a lot of multipath from the GNSS signals. Also very interesting to see how that is changing. Security is something that is increasing more, especially with the view of, okay, we have autonomy, we want the systems to be as safe as possible, and therefore security is one element that also plays a role there. And then there is this reliability concept that I already mentioned to you. We really want to make sure that the system, if it tells you, I am here, that is really trustable, that the truth is coming out of that system. So when we are talking about reliability, then we are talking about, yeah, a GNSS system is affected by multiple type of problems that you might have out there. You might have problems from the satellite, ionospheric delays coming from the scintillation, and now we are in a very nice solar cycle increasing, which gives us beautiful aurora borealis actually in the north, but this also causes a lot of problems on GNSS side. You might have tropospheric errors, multipath, signal masking from the trees, or even some intentional or unintentional type of jamming that might be happening on the GNSS side. So a reliable system, a reliable GNSS really needs to overcome all these type of problems. And this is also what we try to do in Septentrio, to work in all these different areas to mitigate that, bringing a GNSS system that, as an example, has multi-constellation, multiple frequencies that can support anti-jamming, anti-spoofing for those security problems, that can work with different correction services out there, because there is a lot of new correction services popping up, new companies out there. And again, that is still as small as possible and providing you the right interfaces that you can interact for your autonomous system, for your robot, or for your own integration there. So let's go a bit deeper on this reliability topic, and what are the things that we are trying to do in order to mitigate that part. But let's first try to define what we mean by that reliability concept. You can see here in the top you see, well, at some point you have a car. Let's assume that you have a car moving in a curve here, and that car has a GPS, and therefore the bubbles that you get to see here could be the error reporting, the error estimation of that GPS receiver itself. So, what you want is normally indeed a truthful error reporting, especially if you have a bad GPS reception or a bad GNSS reception, and to be able to notify the robot or the autonomous system or the sensor fusion, don't trust me at this moment. This is really what you want. You want that big bubble to give weight to other type of sensors there, because indeed in some occasions, if you are very optimistic in what you are reporting, then you are not really a reliable GNSS system, and therefore you could cause some other problems. Yes, there are mechanisms that you can still do some sensor fusion, but you could still be giving bad information for the sensor fusion and therefore causing some problems that you don't want there. So that's what we are talking about, reliability in GNSS. And you can see some of those here very practical. You can see an example here where you have a GPS receiver car moving from the right to the left side, and well, this is augmented by the way 20 times, but at some point you can see that there is a wrong position reported. The white one is actually the reference receiver, or the true position itself, and you can see that this type of GPS receiver is actually going wrong. It's actually not only giving you a wrong position, but it's also estimating that is actually correct, because you can see the error with the outer lines that you get to see here. Let's see it a bit more in a zoom in here. You can see it here better here. Again, the white is the true position itself. Here in orange, you get to see a position reporting and an error reporting, which seems quite truthful. You see the red one, which looks actually even more optimistic. It says actually have quite good accuracy, but in reality is further away from the truth position. So this error reporting that you have from GNSS receivers is quite important, especially for this topic of reliability there. And this is where we also try to make some differences. Why is this error reporting really important? Well, you can see here, and you guys are many times much more expert than me in all this sensor fusion. And we already heard from the first presentation all the nice things that they are doing in order to integrate all the sensors. But this is what happens. You have a GNSS system, you have an IMU, you have maybe LiDAR, camera, or other sensors, and you are having a sensor fusion, which could be already, as an example, a first step, an INS filtering, which could be, as an example, with products like Movela. And there you are already using the estimation, the error reporting from that GNSS. And again, it has to be truthful as possible. And then you do other sensors that integration with your sensor fusion filter, and you are taking a look at the different type of errors and be able to weight all those different sensors in the different environments that you have in order to have your final output. So again, the better reliability of the GNSS will definitely translate also to reliability of the full either INS system or of the full sensor fusion. So this is really important to take into account. How we do that? Well, it's not necessarily via only software algorithms that you can bring GNSS reliability. You need to do it also in the core GNSS. There are a few core hardware components that you need to do in order to have that reliability side. And just to give you a bit of those examples of the things we try to do, surely, as I mentioned to you, the multi-frequency, the multiple signal, the signal redundancy will help you a lot using some modern signals. So there are different signals. Some signals can even have better multipath mitigation and others, as an example there. The security on anti-jamming protection, error code detection, and different type of algorithms that we can implement on the GNSS system, not only from measurement, but even at position computation level, in order to have that reliability there. So this is really important. Let's just pick up a few of those. I'll pick up now multipath. I think many of you know multipath, but just a quick reminder. Multipath is basically the reflection of GNSS signals when they are coming to walls or to reflections. I can tell you as an example, in agriculture robotics, sometimes you have trees, and trees with water are a very important element of multipath for GNSS, because we have those reflections of the signals themselves. So how can you remove multipath or mitigate that multipath error? There are different type of techniques, and here I just grouped 3 elements. One could be the design of a new signal system. As I told you, there are certain signals that are capable of handling multipath in a better way. As an example here, the BOC BPSK signal that you may have there. Another mechanism could be indeed using other signals, other type of backup signals, or correlation techniques, which is mainly algorithmic type of elements. And the third element is, okay, you have a few antennas in the market that can also reduce the multipath effects as well. So it's of course a choice of different type of things you could do, but what we try to do in the GNSS receivers is to implement some of those things. As an example, here you can see multiple signals. So this is actually in a receiver. We really try to bring all those signals availability to even be more resilient against those type of reflected signals that you may have from the environment itself. Again, with all this type of machinery, automation happening in robots or big machinery, there is a lot of reflections that we get to see. So multiple signals will help a lot. And also, of course, we have a few algorithms. As an example, here you can see how we can reduce the multipath using some proprietary algorithms in the GNSS element. So that makes a difference, of course, again, on those difficult environments where the GNSS reception is not ideal. And then also briefly on the security and resilience side, well, we get to see this more and more. We get to see customers integrating autonomous technology having problems of jamming and spoofing. And unfortunately, this is happening more and more due to the geopolitical situation nowadays. But yeah, I will explain some of those problems in a minute. What's jamming? Just very quickly, many of you know it, but it's actually destroying the GNSS signal. So you have a transmitter that is operating in the same radio signals or frequencies of the GNSS, which is stronger signal, and therefore you cannot listen to that signal anymore with your receiver. So this is why you can see here in the graphic, it really destroys the signal when it's coming. And you have this type of devices, by the way, you can use. Now you can buy them for 20 euros actually online, and then you can create a jammer that can operate even to far distances, which is actually very interesting to see. And then you have spoofing. Spoofing is something that became very popular with the Pokemon Go, but it's basically sending a signal that pretends to be the authentic signal of GNSS, but in reality it's a wrong signal or a fake signal that is taking you from one location to an undesired location. And this is something you will not want to do, and this is happening more and more. Before, spoofing was really not happening, but the technology to make spoofing became also quite available, and the fact that there are more robots out there is also creating a big problem. Now imagine your robot or your mobile robot suddenly going to the wrong location because somebody is spoofing it in the near location there. So it's becoming a problem. So let me just talk about jamming and first, and then a bit more on spoofing. For jamming, what we get to see is there are different types of jammings out there. Again, as I mentioned, many robots, many drones, they have self-interferences. So this is what we would call in-band interference, and these harmonics and these signals that are coming very close to the GNSS, and therefore you have problems of your robot operating in some occasions, and that happens a lot. You could have also unintentional jamming coming from the outband interferences, which could be cellular, satellite communications, UHF. I mean, you have a lot of communications in your robot sometimes. Those could also create some unintentional jamming. And then you have, of course, the intentional jammers that can go, of course, from these small 20 euro jammers to very complex jammers. So when a GNSS receiver tells you, yes, I'm jamming resilient, you have to be careful because not all will be able to cope with this different type of jamming scenario. So we use different type of techniques, both in the hardware as well as in the software, in order to try to mitigate those jamming scenarios. And yeah, they prove quite effective in our technology. We are happy, very happy that this is even tested by third parties, and it's quite well solid technology behind. For spoofing is an interesting problem, especially with when talking about sensor fusion, because you have normally a flag that tells you, you know, I'm in a spoofing moment right now. Here you can see, as an example, a spoofing attack. And then you have certain receivers that sometimes might detect the attack, or maybe they will not even detect it at certain moment. So the reliability of that spoofing flag is really quite important, because then you can tell either your INS or your sensor fusion system that you cannot longer trust the GNSS. So this is also very important, and we are really trying to make sure that that's quite reliable in our side. You can see here, as an example, the impact that you have in an INS solution. Many people think that INS is solving the problem of spoofing. Yes, there are mechanisms to detect that the GNSS is moving from one location to the other, and therefore you will detect spoofing. But if these spoofing is done in a very gradual way, as you can see in this example. You could take an INS system from one location to an undesired location. While if the GNSS is reliable flagging that spoofing, then you will be in the blue line here, which is spoofing is detected, and the INS system or the sensor fusion will be able to cope with that spoofing in a good way. Other elements of robustness, by the way, just to mention, I mean, when you are talking a GNSS system in an autonomous system, that vehicle or that robot is operating in multiple tough environments, and there is a lot of vibrations in a few occasions. Some people think, a small robot is not really vibrating a lot. Or you can see here, there is rough terrain in many occasions, which also could trigger problems with the GNSS technology. So you need to have reliability also in the choice of the GNSS that can bring you a good robust solution for the full robot itself. And this is my last part, just going very briefly on the integration with Movella and some of the data actually I got from, thanks to the team from Movella. But the beautiful part is you can integrate a Septentrio receiver together with the Movella systems. You can see here how it's integrated. It's actually using the Septentrio binary format, which is coming out of our GNSS receivers and therefore integrated already thanks to the support of Movella in their INS systems. So you can do that for the MTI 670, 680, or even for the MTI 7 and 8. So that's all available as an external GNSS system integration that you have. And they have done a few tests that you can see here as an example, comparing a Septentrio RTK receiver combined with the Movella system versus other high-end RTK systems. There you can see that, therefore, in this example is actually showing the value of the high update rate that you can get with this combination. Another example here is in a difficult environment, which is actually a bridge of 58 meters. You can see very nice pictures that they were also making. And you can see here again how the combination of having a reliable GNSS with an inertial system can bring quite a lot of differences in the final solution itself as well. You can see again the dark blue, which is actually the combination of these two systems here. And another example again with dead reckoning. Again, a bridge that you get to see here, 21 meters. And again, you get to see how that reliability definitely also can help into the final solution itself. So these are very nice examples. Again, thanks to Movella for providing this test. And how will you integrate it? Well, you have two options. Either option one is you have a dev kit from our receivers that you can use together with the dev kit of Movella. This is fully documented in an article that you will find online. Or option two, we just did actually an open source project which is integrating the Mosaic in a microbus compatible board, and that's actually the pin compatibility that this type of boards from Exens Movella are using. So definitely is an option too. But again, option one is already fully documented, fully working, and yeah, we are definitely welcoming everybody that might have questions on that. Again, reliability can be quite important, but to predict the future is up to you. So I'm sure that you will come up with a lot of exciting applications in integrating either GNSS or INS systems there. So I don't know if there are questions, Minder, at this moment.
Yes, muchas gracias, Gustavo, for your presentation. And indeed, there's a couple of questions came up. I will address two of them because we only have 3 minutes left. The presentation took a little bit more time, but that's okay. We will answer in the end all the questions that have been asked. Yeah. The first came from Dennis. So you write on slide 13, you write centimeter accuracy. How much is centimeter? Is that 1 centimeter? Is that 10 centimeter? Can you shortly?
Yeah. So when we are talking about RTK, we are talking about 1 centimeter accuracy. That's for sure.
Yeah. Okay. And then Mirko asks, sorry, to go shortly back on the 1 centimeter. I think you have a CEP qualification on this, right? It's an average centimeter accuracy. That's what you use.
Yeah.
CEP. Mirko is asking, which algorithms does Mosaic use for error reporting? Are they public or are they referred to accepted scientific literature. So we're talking about here about the covariance output,
Yeah.
right?
Yeah, exactly. Which is actually a bit on this side. These are all the different kind of recipes we use. Some of them are standard things like multiple signal, etc. there, but using all those signals inside the system is proprietary. So for instance, for multipath, we have an algorithm patented, which is called APME, which allows you to mitigate those wrong signals there. So I would say that's the more important there. But we have other technologies. As an example, for the ionospheric conditions, we have also another patented algorithm called Ion Plus, which is also helping you there. Same for the resilience, spoofing, jamming. There is a lot of proprietary algorithms. For the basics of certain things, we try to use, of course, some open literature there, but there is a lot of private IP in many occasions.
Okay, then I will move to shortly intermezzo also on Movella. I hope my presentation works. Yeah, there we go. So first of all, Gustavo also mentioned already Movella and Xsense and how is this now related? We get questions, of course, of people who were not updated on this. We all probably know Xsense, but Xsense has been fused. The company has been fused with another small companies, and this all has become Movella. So it's simply a change of name, but for the rest, it's the same products that we are providing to our customers. So if you read Movella, you can also read Xsense if you are looking at the MTI series of products. The MTI series of products, that's what I will shortly also address here to show you the latest developments that we are doing. Basically, what we do is sensor fusion within one sensor. We combine those gyroscope accelerometer and magnetometer data in combination with position from GNSS and the barometer. We combine that and we do real-time sensor fusion. And this sensor fusion, we use it for multiple sensors on the body. As you probably know, our products like MVN, where we are market leader in the mocap market, used in film studios, in gaming, but also for human motion measurement in rehab situations. That's where we use those sensors to map the biomechanical body, to map those sensor data on the biomechanical body. So that's why also it's sensor fusion within the sensors that we are doing. The sensors that we use for typical equipment, motion tracking, or digitizing the moment are called the MTI series. For the people that didn't know yet what MTI means, you can see it on the bottom. It's a motion tracker, industrial. And as you can see, these are typically applied not only on land-based vehicles like we are treating today in this conference, so outdoor and indoor ground vehicles, AGVs, AMRs are typically used indoor, but outdoor there's many other vehicles like in the agricultural scene, like in person transport or goods cargo transport scene, container terminals. That's typical ground vehicles that are also need the digitized movement data to either autonomize the vehicle or make it more safe or more efficient, and in this way support the operator of the vehicle. The other markets that we are also serving here, you can see the service vessel and also buoys and typical underwater robotics. It's also a very interesting scene where a lot of innovations are taking place. And the last is also flying, like Gustavo also shortly showed in his presentation, like last mile delivery of packages and these kind of drones, but also other drones like for surveying areas. So these are typical applications and markets that we are serving with the single sensor modules, the MTI series. A little bit more detail on this MTI is basically the data that we are providing to our customers' subsystems are 3D orientation and global position data. So what is 3D orientation? 3D orientation is typically the roll, the pitch, and the heading, but so the angles, but also linear acceleration over X, Y, and Z. So So it's the orientation of the device, and the orientation of the device, or the vehicle in this case, is mapped basically on the earth-fixed frame. They call it ENU, so that's east, north, up frame. And we basically give you the position of the vehicle on that frame. So that's 3D orientation. So that's something else than 3D LiDAR. That's not completely the same, but it's both 3D. And in addition to the 3D orientation, we provide our customers with the global position data. As also the previous presentation, but there's also different brands of GNSS, of course. And this is typically the position of the vehicle relative to the geographic coordinate system. So latitude, longitude, and also an altitude indication. So what does this look like in detail in our sensor? We can offer our customers different levels of data. Some customers say, hey, I just need the raw data from the gyroscope and accelerometers. I will do my own Kalman filtering. That's fine. We will supply to you an IMU. That's the basic level of a typical inertial measurement unit. And it's raw but calibrated data that our customers use to determine the 3D orientation of their vehicle. The next level, when they start using our Kalman filtering, also the Xsense Kalman filter algorithms, then you get from the same sensor, you get the roll and the pitch angles, and also the unreferenced or relative yaw in the flat plane, which is typically used also for navigation. And that's what the subject of this conference is. Again, a next level is also we start using the magnetometer. So you also have absolute north referenced heading. So not relative angle, but absolute north referenced. And then the next step is to use also your GNSS data when you are outdoors. And we can improve the 3D orientation data, and we can add also position, velocity, and sometimes also necessary for customers, the GNSS time being the master clock of their system. So in this case, we can offer even more data for the vehicle. One level higher, and this is really coming up the last years, is to have this position also centimeter level accurate. And what we do there is also small temporary dead reckoning. So when you have a bad GNSS connection, like Gustavo already indicated, can be multipath, can be other reasons why the GNSS connection is bad. Using your IMU, we can do some more dead reckoning. And also we can provide a higher rate of data, which the subsystems of these vehicles often need. They are using LiDARs, they're using cameras, very high rate data, and these all need to be synchronized with your own orientation. So this is under good GNSS conditions, clear blue sky. That's why I put the clouds there. I got some questions. Hey, that's nice, some clouds, but what does it mean? It means that you have good connection with your satellites. At least 2 or 3 would be even better, and then you can do your triangulation. But what if your connection with the satellites is not so good? So you are, for example, under a canopy of trees, or you're going into a tunnel. What should we do then? Well, we can still provide you with centimeter level 3D position, still real time and with a low latency or low delay. But we are using a dual antenna when you have still good GNSS position, but mainly we are starting to use also a camera. Like we do as a human being, we use our eyes to determine our speed and to determine where we are. We use it as part of our navigation. And the same thing we can do also now in the sensor world. And we are doing this with our partner Fixed Position. They will later on also present more details about this product. And you see also this small wheel odometry measurement. Yes, also wheel odometry. If we're talking about a ground vehicle, we can input the wheel odometry to further improve the velocity estimation, and therefore also your new position if you don't have a good proper GNSS connection. So what does it look like? Well, typically if you move the MTI, so I'm not talking about position here, but only the 3D orientation, this is typically what happens, and this is the data that these autonomous vehicles use in navigating, and especially challenging environments like Nicolas already indicated, with high slopes and bumpy grounds. There's very important to know real time what is happening to the vehicle. So here you see the lineup. I will not go into further detail, but basically it's all the different data functionalities from the basic IMU to really sensor fused data. There's different form factors. So if you want to just plug it on your vehicle, screw on and off you go, or you want to deeply integrate it, then it's also possible going to the more OEM versions on the left side. These products come with also application software, so it's easy to take the data, to set the sensor up, and to start using it. If you have any further technical questions after you have acquired the sensor, we have a very nice platform which is continuously maintained by our field application engineers. They talk with all the customers out there. We have more than 1,000 different customers. They all give us feedback, and we can use that feedback to improve the product. And this is typically what we are trying to do also through our field application engineers. They update all the data in there. It's all available, and basically, yeah, the customers can use it, do it all by themselves. Sharat Kumar, if we take raw data from the Xsense MTI 710, specifically accelerometer, gyroscope, and magnetometer data, do the data also include noise, or is that noise removed? Yeah, so the sensor data is calibrated and the noise is still in there. Daniel Reyes, does each sensor series have different component characteristics, quality and accuracy, or are all the same, just different functions? Good question. So basically, within the series, because we have different series, 1 series, 600 series, and 100 series. So that's the first number after the MTI. That number indicates, if that number is the same, then also the sensing elements in the sensor are the same. So quality, accuracy are all the same within the series. That's the answer to this question. So an OEM version of the 630 AHRS is doing exactly the same as the rugged version 630R. Is there any model that includes already the RTK GPS, Teresa is asking. Yes, absolutely. MTI has the MTI 680G, which includes a GNSS, an RTK GNSS receiver. And you can provide the sensor with the correction data, and then you will have your centimeter accurate position data. So, Bernard, what is the drift if there is no GPS signal at all? That really depends on your movements, first of all. And we will use the movements, so the linear accelerations, to determine the new position. There is drift. And there's also drift over time, but this can be reduced by, like I said, also to start using the camera. But we will output the position for about 20 seconds after GNSS is lost. And then you will get drift. And of course, as you know, it's the same as if you walk and you close your eyes, then you will have error on error on error, and your drift will become bigger. You can't correct it. So that's why we really advise also after a couple of 20 seconds and you do a lot of movements, then the drift will of course increase. But it depends really on your velocity and also your linear movements. I would say test it and see if it fits your application. So Laurent asks, what is the price range? Well, the price range goes from, it really depends on which form factor you would like to use, right? And also the accuracies, but it goes really from below 100 euros to above 2,000 euros. That's roughly the price range where you can think of. But don't hesitate to contact us because we have, of course, also, if you use more sensors, we do volume pricing. So let's just talk about this, and then we can exactly determine which one you need and what the price would be. To announce the next speaker, which is from Intralogistics. Daniel, are you with us?
I hope so. You can hear me.
Yes, we can hear you. Thank you very much. So from the cold Netherlands, we move to the cold south of Germany.
Myra, thank you very much for the introduction and especially for your presentation before mine, because so I don't have to tell people where your XSense sensor is used in our robots. So first, some words about Intralogistics. We are founded already 2012 in Bavaria, have actually 35 full-time employees. And our last financing round was, oh, here's a small mistake. It was December 22. We raised 5 million euro. And with our autonomous mobile robots, we have applications in a lot of research in nearly every industry, from manufacturing to logistics, health, food, everyone that has transportation. Yeah, so we have customers in a wide range of industries. And what's so special for Enog? The first point is the most important. We can handle missions indoor and outdoor. And we don't need any special signage or modifications to the plans. So we don't need any modifications in plans or special signage in plans so that our robot can navigate. We use a very complex portfolio of sensors, and the XSense is one of them. Yeah, that's something I think you know the market for autonomous mobile robots is extremely increasing, and yeah, with our transportation robot, the Enduros, we play with the most growing fields. This is where Enog is coming from. The initial product, the platform, is the Heros. This is available as two-wheeler, four-wheeler, but the Heros is the scalable and flexible robot platform for our autonomous mobile robots, and especially all-terrain robots in indoor and outdoor areas. And what's special for Enog is we are one-stop shop. So you can say we have our in-house production, electronics, software development. We put in the sensors. We have the integration. We make maintenance and service. So yeah, we have everything in-house. And the Heros is the platform for our two main products. So the Heros itself is a main product. It's especially used in a little bit name dropping in every famous university or research facility. The RWTH Aachen has an Heros. The TUM in Munich has two. So a lot of research organizations and universities has an Heros from Intralogistics. And we built our two main products out of this Heros platform, and it's the transportation robot, the Enduros, and the irrigation robot, the Rhinos. It especially irrigates graveyards. So let's dive into the Enduros, our transport robot for indoor, outdoor, or combined missions. It's extremely robust for all weather conditions, poor soils, or ground sills, so every ground conditions. And it's capable, it's for autonomous coupling and uncoupling of trailers. You see it in these pictures, and I show you a video also after this slide. And the special thing is, and this is also where the Xsense sensor is one part. We combine a lot of sensor technology in our robots. In this picture, you can see a safety scanner, and at the bottom of the robot, we have a lot of sensors under the hood. You can see a LiDAR on top. And this sensor combination we call analog hybrid navigation. So we don't need extra markings or modifications like electronic cables on the floor or something like that. We all don't need that. And the robot can also charge inductively. The video is without sound, but I tell you what you see here. You see the Enduros driving outdoor. That's the company Rigdon, a tire manufacturing company that's using the Enduros for transporting their tires from outdoors to indoors, from indoors to outdoor storage. And here you see they have a very bad floor, but the robot has no problems with it. It's here you can see the autonomous coupling and decoupling. Here again, the bad floor, and this is soils. And it's super secure. Here you see the employee jumping in front of the robot, and this immediately stops. That's what the Enduros is. And our second main product is the Rainos, the irrigation and watering robot. And coming to the Xsense technology, we use it especially for as an IMU for accelerometer, gyro, odometry data. So inside our complex setup, especially when you're driving outdoors for INOG, it's extremely important to have the data, what the robot itself is doing, not only where he is driving, but also what he is doing, how he itself is moving. The Rainos is especially for cemeteries. He can water up to 15 hours a day, or especially at night where no people are on cemeteries. But we also have some cemeteries using it a day, advertising, using it for advertising. They say, hey, I'm watering your grave. If you also want that I water your grave, call my owner. So the Rainos refuel autonomously at the watering station. It's super easy to use with our INOG graphical user interface, where you only need a web browser to communicate with the robot. You see this interface in the upcoming video. And also this robot has the same high security standards, even higher than a little higher than the other robot. So I will also show you a short video here. Initially, this is a use case video, but it shows here you see how the robot is moving and where we need the sensor data. And it's, yeah, you don't need perfect ways it can drive on every floor, every area in the cemetery. And here the owner of the robot is telling how he is solving a lack of personnel with the robot, because people that caring for graves to find this is very difficult. The same with the transportation robot. The people where the robot is doing the job of some people, those people can do work that's much more worthy. Here you see our graphic user interface where the robot is driving, and yeah, so the robot is saving time, very efficient, and people can care for other more important work on graves or for the transportation robot also in the facilities. And yeah, he's asked how people react on the robot, and people love it, even on the cemeteries. And here you see it driving and watering at night. And that are some of our customers. So yeah, with the heroes, I told you, the University of Aachen, the TUM University Munich, Technical University Berlin is using the heroes platform. And we have a lot of cemeteries using the Rainers. Actually, also the first in Switzerland. We are not allowed to tell the names actually, but we have the first customers in Switzerland already, and the same with the transportation robot, the Endurus. It's used at Daimler, Nokia, Total Energies, but also extremely successful companies like Zwickau, Rigton, we saw in the video, the company Landguard, we also saw some pictures from, and we have actually the number 70 is not right anymore. I think it's over 80 mobile robots we have running outdoor and totaling operating hours. I think it's around 200,000 actually. And yeah, here it's interesting. We asked the responsible person at the company Landguard how satisfied they are with the robot, and they said our main problem was how would employees react on the robot? Can it integrate in our company? And after the first week, he says people were super happy. The robot was extremely well integrated in the company and what they do. So a very big success for us and for the company, for the customer. Yeah. So yeah, I think it was 50 minutes, perfect on time. Our mission, yeah, we help companies to protect and utilize their highly skilled employees for more value-added activities by automating stressful, hard, dangerous, and time-consuming tasks with our AMRs, our autonomous mobile outdoor and indoor robots. And we are on the way to establish the best in-class AMR platform. We are rapidly expanding our network of strong service and retail partners, and we project a turnover of 50 million euros in 2025. And if you have questions, I'm open for your questions now, and you can also contact me later by my email address, daniel.brandt@intralogistics.de, or you can directly also contact me on LinkedIn, where you will find me. So looking forward to your questions.
Hey, thank you very much. I have a couple of questions that I'd like to address, some more technical ones and a little more high level. I'll start with the high level one. The first one is, what kind of certification for fulfilling safety demands was performed on your robots? Because it's also operating in an area where people are walking around, I guess.
Yes. Yeah. We have special safety scanners coming from another company, that name I will drop here, but we have special safety scanners, and we fulfill safety norms and certifications like the classical DIN norms. So we have class certifications for safety and security.
Mm-hmm. Okay, thank you very much. That answers 2 questions, actually. Also for Christoph, he had the same question. And then Art has the question, how do you take the dimension or the properties of the trailer into account in your navigation algorithms? So the thing that's...
Yeah, we the customers that buy our robots, we visit them and scan the area where the robot is used with a special 3D LiDAR imaging, with a very special scanner from the company Regal, and the dimensions where the robots, so the place that the robot needs to drive and transport the wagons or transportation wagons is, let's say, about 1.5 meters in wide, but we can also handle dimensions of less space. You can check our YouTube channel. There's a video from the company Zwickröll. There's the robot driving in very narrow, small areas, also outdoors.
So you do take into account as a preparation the length or the size.
Yeah, absolutely. If the wagons we are pulling are much more in length, we need a little more space. But there we have also an interesting video published. I think it was last week. We have one robot running at Kubota, the industry machinery manufacturer Kubota. There the robot is pulling, I think it's 4 or 5 material wagons at once, where you can see how much space he needs, he will use. The robot is also capable of opening doors automatically in this video. I think who's interested in it, check our homepage, our YouTube channel. There you can see the space the robot needs.
Okay, clear. So this also is a good link to the question of Jeffrey. Jeffrey asked, so how is the indoor navigation being performed then? So which sensors in the navigation stack do you use, and how much weighting do you give to each sensor in the sensor fusion? So for the indoor navigation, right?
Yeah, exactly. The indoor hybrid navigation, that's what we call hybrid navigation, uses more sensors at one time. So we can use the security, the LiDAR, the Xsense, the imaging sensor at the same time. But when it comes to driving outdoors, we can also add GPS. We can also use Wi-Fi. So we have a broad range of sensors that we combine, and this hybrid navigation, we call it, is using a lot of sensor data at the same time. So we don't, so with our robots, you don't have the time where the robot it's using LiDAR, then it stops, then it's switching to imaging sensors or GPS sensors. That's not the way our robot works. So it's this hybrid navigation is using a lot of sensor data at the same time.
One of the questions, the battery of my iPad lost, but I remember the question was about how do you switch between the indoor and outdoor environment? Do you use a different sort of navigation stack? Or is that seamless?
It's seamless. But sure, it's the LiDAR scanner is used outdoor as indoors, but some customers want to navigate with GPS outdoors. Some say we have a very good coverage of Wi-Fi. We use this technology. So that's what we call hybrid navigation. We can use a lot of sensor data at the same time, and when we move from indoor to outdoor or from outdoor to indoor, the used sensors switch, but without waiting time. So when the robot moves from outdoors to indoors, he's not stopping when he's switching sensor data.
Yeah, exactly. Yeah, because that's also one of the questions from Patrick. Are you working with static mapping techniques? But how do you deal then with the dynamic changes in your path planning, etc.? So this is typically
the robot is also capable of SLAM navigation. So it's not only static data.
No. Yeah. So you have a map already that you use for reference.
Yes.
And this is
especially the map is a big benefit of when you start initially teaching the robot where he's used. But when we have modifications, like something is in its way, people are moving, the robot is using all the sensor data real time.
Okay. Okay. I don't see different questions popping up. I have one question myself. So I saw the spraying robot is moving really slow. The pulling robot basically is moving quicker. What is the maximum speed that you would normally go if you go indoors versus outdoors?
It depends on the gearbox. The transportation robot can move up to 6 kilometers per hour. We sold some that are also moving faster, but that's the standard between 3.5 and 6 kilometers per hour for the indoor transportation robot.
Mm-hmm.
And the outdoor transportation robot is moving slower because it's moving on such bad soils, like the grass, holes in the soil. So he has to move a little bit slower because he's carrying 250 liter of water with it.
Mm-hmm.
So he has to move a little slower.
Yeah. Okay, good. Thank you. Okay, so we will now move to Switzerland, near Zurich or in Zurich. We have our partner for the VINS solution, basically, which is fixed position. So Peter, if you are ready, please go ahead and start your presentation, and you have some extra minutes, 5 minutes extra, so you can really take the time to explain your challenges that you and how you solve them.
Sounds good. Can you just confirm you can see my full screen?
Yes, I see a nice picture of high buildings. I don't know, I can't see what city it is exactly. Is it a real city?
It's not a real city. It's not a real city.
But it shows the challenges that you are facing indeed. Okay, thank you. Go ahead.
Great. So, good morning, everyone. Today I want to tell you a bit about how vision can enhance GNSS applications. We heard some great stories this morning about the implementation of autonomous robots and the benefits of using GPS. We also heard from Septentrio about the importance of resilience of GNSS. GNSS is one of the best technologies out there for scalability. It's very precise. You can get down to centimeter accuracy with RTK GNSS. It's available. You get global position and orientation, and you get that directly. And it's very scalable. It's low cost, it's computationally efficient, and it doesn't require mapping or anything. So from the get-go, you have a precise solution that tells you where you are at all times. Vision, or visual inertial odometry, has other benefits. It's robust, so you can navigate indoors, you can navigate through urban canyons, you can navigate in dense forests, through orchards, and you always have a good pose. You get real-time high frequency and low latency pose estimates, which is one of the shortcomings with GNSS. And it's self-contained. It doesn't require any external infrastructure, any beacons, any satellites, or anything of the sort. But both of these technologies have their own shortcomings. GNSS, while it's great in open environments when you have good satellite visibility and good corrections, it can have issues with signal interference, with obstruction. In certain environments, you see that it has very limited accuracy in urban canyons, in orchards, close to buildings, and even in areas where you might have poor coverage of either RTK correction services or a 4G cellular network to receive those corrections. So it requires the corrections, and that's one of the weaknesses. And it does depend on external signals. So as soon as you're going indoors, it's not very useful. VIO also has its shortcomings. I mean, there's a limited operational range, and drift accumulates. So you have errors over time. Of course, you can handle this with mapping, but it's computationally more complex. It can take a lot of resources. And in addition to that, maps can change. So when you're navigating outdoors in environments that are very open and you don't really have features to track, or in environments that are changing a lot, this can be in agriculture because from one day to the next, an orchard has had all its fruit picked, or because it suddenly snowed. There are challenges, and there are challenges with initialization and relocalization. So how do we overcome these challenges? Well, we at Fixed Position are focused on a number of things. We are GNSS experts, we have vision experts, and most importantly, we do fusion. So we harness the strengths of different technologies, we take that raw data, and we combine it into our XFusion engine. And this allows us to provide a very reliable position and orientation. We take in raw RTK GNSS data, we take in raw IMU data, and we take in raw tracked features from our visual odometry front end. We can also add in other sensors where necessary, for example, a vehicle speed estimate, either through wheels, through radar, or anything of the sort. And we leverage all these different sources of information to overcome respective weaknesses. So how exactly does our fusion work? Kalman filters are typically the most standard solution out there. However, Kalman filters have issues. One of them, for example, being the fact that it's less scalable due to large-scale problems with EKFs. They don't handle nonlinearity very well. They will struggle if your environment is changing a lot. I mean, the dynamics of the environment or of the platform. So it can be overly focused on the tuned environment and vehicle, and it's less robust. What the benefits of the factor graph are that we have a probabilistic model that represents a lot of variables and measurements in a whole system. And these variables allow us to very accurately, over multiple states, keep live information about where we are and where we're going. So by having this closed loop function in our factor graphs, we're able to correct errors, re-optimize for past states that are still open. And that means we can correct errors retroactively, improving our overall accuracy. It also ensures consistency in the estimation approach, as new measurements can refine the entire trajectory, not just the current state. So our optimization approach ensures this consistency and increases the stability with a fixed complexity. So how do we do this, and what exactly is powering the XSense Vision Navigator? Well, in the XSense Vision Navigator, we have a number of sensors already embedded. This includes a camera, IMU, 2 GNSS receivers, and we have a positioning engine. Now, our positioning engine is able to run on this low-end compute system, which is a challenge, and run this in real time to give world-class performance in terms of pose and velocity estimation. So the XVN is one of the best solutions on the market to use in environments where dead reckoning is necessary, where GNSS alone might not be helpful, where mapping might be complex, or where you might be navigating between environments where you can map certain indoor areas, but outdoor ones might become too complex or changing too rapidly, or even if you need some redundancy there. But in practice, getting such an optimization to work well is very complicated. So we need to train our algorithms to be able to adapt to the environments and platforms on which they're being used. Now, the XVN doesn't automatically record any data, but customers that have challenges in different environments, they are able to record the data, share it with us, and we can train our algorithms and redeploy that to all our customers to improve these corner cases and ensure best-in-class performance in a variety of environments and a variety of platforms. So these platforms will include platforms in urban settings such as delivery robots, street sweepers. They will include tractors that are navigating through orchards, lawnmowers. There are a multitude of applications here. So how exactly does this retraining of the model and deployment help? Well, it helps us, and we heard about this challenge earlier with Septentrio, identify spoofing and reject bad GNSS. We're also able to identify false fixes, and this is one of the things that Septentrio was correctly pointing out, is that sometimes you can have measurements that are inaccurate, but they tell you they're very accurate. So when I talk about a false fix in the sense of RTK GNSS, I'm talking about an RTK fix where our GNSS receiver tells us it's certain of its position down to 2 centimeter accuracy, and actually it's maybe 1, 2, 3 meters to the side. So thanks to our complex models and these different sensors embedded, we are able to identify these measurements, reject them, and adjust our covariances as a result. Our optimization problem actually contains hundreds of parameters. So when I talked about this factor graph optimization, you hear a lot of academic papers in deploying this, and it can work well in certain settings. And for academic purposes, you will have a specific example where it works really well. But deploying this into a product in the real world, where platforms change, environments change, where they're confronted to different issues with measurements, whether it's from the camera having interference, from objects moving in front of it, whether it's GNSS having interference, is very complex, as well as I mentioned the dynamics of the platform or changes in the environment. So these hundreds of parameters allow us to represent different models for these changing vehicle dynamics, environments, and much more. We're able to improve this with our machine learning training methods and have models that allow the parameters to self-tune dynamically in real time when necessary. What does that mean? That means, unlike a standard application where you choose one tuning mode and your vehicle is using that, we've developed complex models that represent underlying use cases. And within those models, we have self-tuning parameters that might adapt in real time. So for example, if you have a vehicle that at one moment is driving at 2 meters per second and later will be driving at 20 meters per second, some of those parameters will adapt because the way the vision and parallax is changing is going to need to be handled differently. We also have different time to do computation in those scenarios. The IMU dynamics might be different. So we have developed very precise models to represent this. And this has given us the ability to refine this. We've collected tens of thousands of kilometers of data from all over the world, from various different locations, environments, use cases. And this has allowed us to outperform classical rule-based approaches by more than 70%. So what does that look like when we look at some statistics? And why should you choose the XVN over a standard high-end GNSS INS solution? Well, here we look at the error as a percent of distance traveled of a standard high-end RTK INS system. This is representative of a $20,000 high-end RTK INS system. It's very useful in certain circumstances, but here we took data from about 800 kilometers of randomly selected data sets with ground truth, and we looked at the errors in areas where GNSS had outages. And we considered GNSS outages anywhere where GNSS was no longer useful for the dead reckoning. We had to rely almost purely on VIO or INS solutions, because if you have bad GNSS 3D or RTK float GNSS, you might have GNSS that's only accurate from 5 to 20 meters, and that doesn't help if you're trying to maintain centimeter accuracy. Now, this data is compared to the post-processing of the high-end RTK-INS solution. So here we're looking at the percent of error as a percent of distance traveled of the high-end solution against its own post-process result, and the same for the XVN. So the XVN is compared to the post-process result that was used as the ground truth, and it's the post-process high-end and not the XVN's result. So there's a tad skew to benefit the high-end system in this case. So in an outage, what's the probability of your error being less than 1%? Well, in most cases with the high-end solution, it's close to 25%. With the XVN, we're already looking at a close to 80% probability. Having an error below 2%, with the XVN, we're looking at a close to 95% probability. And below 5% with the XVN, you're almost certain in all types of outages to have that reliability. If we look at the metrics in terms of mean, median, and standard deviation, we see a significant difference. The mean of the XVN is well below 1% of distance traveled, and more importantly, the standard deviation is also well below 1% versus high-end solutions that can have the high 6 to 10, 20% errors. More than that, the XVN doesn't suffer from time-dependent drift as a typical INS system would, thanks to the use of the vision to identify when it's moving slowly, when it's stopped, and it only accumulates drift with distance traveled. So I want to take you through an example last week of our colleagues driving through an urban canyon in China and what that looks like. Here we can see on the left side of the image what the camera sees. You have a lot of traffic moving around, you have cars, vehicles. On the right, you will see the XVN performance and you'll see the RTK GNSS. So we just went into a tunnel, the GNSS completely disappeared, there's no more signal, you have nothing at all. All of a sudden, the GNSS comes back, but it's 20, 30, 40 meters away. Even here, we're still between canyons, the reception is still bad, the GNSS performance is still at the 10-meter level, 3-meter level, and only once you get to open, it rejoins the XVN's position down to centimeter level accuracy. So just to highlight what this exactly means, here we have an example of a typical drive in an urban canyon in China, where you go through tunnels, you go through a number of areas where there's just no GNSS or you have a lot of multipath. And you can see that you have huge gaps of no position and you have a lot of areas where your position accuracy is at best 10 meters accurate. The XVN allows you to maintain high centimeter accuracy throughout those areas, and this includes these heavy multipath regions. To give you a bit more insight, if you look at the area on the right, you see a lot of multipath. You see the XVN performance. If we zoom in and just give an example of this, we can see that over a 1 kilometer example of multipath where the vehicle turned around, came back, you see when it rejoined on the left, the RTK fix, the XVN was still centimeter accurate, whereas the GPS in this situation was accurate on average 4 to 5 meters throughout this trajectory. What about other use cases? Because as I mentioned earlier, the XVN is used not only in urban canyons, not only in cities, but also in other applications such as agriculture. Well, we heard earlier this morning about the benefits of agriculture and some of the use cases and how you can do row detection to maintain your position in the row. But it can still be a challenge if you're navigating through orchards where your position is way off, that might show that you're 1, 2, 3 rows away and you don't know where you are. On the left, you'll see this is data we collected a couple of months ago in the US in some dense walnut orchards. And you can see on the left that the GPS alone really struggled. And in fact, at times it was 2, 3 rows away. So the system had no idea where it was. And on the right, you can see the XVN was able to maintain really accurate positioning throughout, enabling better control, better performance, and increasing the operational viability for these types of applications and for our customers. So by providing this reliable and accurate GNSS or position at all times, our customers are able to significantly simplify the control problem and really focus on deploying and getting to market quickly. So now talking about deploying the XVN in the real world, if you want to see this for yourself, if you want to experience this in real life, please get in touch. You can request a live demo today. Just email support@movella.com and we'd be happy together to arrange any sort of demo for you so that you can experience this for yourselves. Thank you very much.
Thank you, Peter. Excellent. Some nice practical examples in the challenges that we all are facing to navigate our mobile robot. I have a couple of questions also for you. The first one came from Fatima. She asks, what's the kind of application more safe and secure for autonomous railway? GNSS INS or VINS? It's a little bit also, I think, from my original presentation, but you probably also have a very clear opinion on that.
Yeah, so this is always a complex topic, and we've been approached by a lot of railway companies for this. And I don't have the full answer for this. I'm not the expert on railways, but I'll tell you a combination of the two is typically what works best. We've done a lot of tests on railways, and we see that GNSS plus VIO, so GNSS VINs, is what's best because it covers these large areas, but also gives the ability to truly perform well in areas where you might have a lot of metal that blocks good GNSS signals when you're going through tunnels, while continuing to rely on GNSS itself when you're moving through these very open areas at high speeds.
Okay, thank you very much. Jules, Accent's Vision Navigator seems great to work both indoor and outdoor. Yeah, comment on that. It's true, but basically the focus is outdoor and you can go indoor also, or you have indoors like situations. So his question is, can it handle the robot also starting indoor and initialize it to a given position without having the GNSS RTK fix?
That's an excellent question. Currently, the VIO aspect, we do no mapping at all. So it's completely an estimated solution, and we're talking about relative positioning as soon as we lose GNSS. So our localization and relocalization happens with the GNSS. However, we are currently working on a feature that will allow our customers to input, to initialize by inputting a known pose estimate into the system, so a known location and orientation, and we'll be able to initialize from that. And that will be available very soon, towards the beginning of next year. And why is that? Because we have a number of customers that do use our solution to go indoor and outdoor. They might make their own map indoor, and from that want to initialize there, feed it into our system, and then already get that position as they navigate through the world indoor and outdoor.
Yeah. So it's also, you call this the indoor start feature, right?
Yes, exactly.
So this exactly addresses the question of Jules, I hope. Jules, if you have any more questions, don't hesitate to contact us. Patrick, how do you deal with different light conditions, like at night, for example, or rain and snow conditions? Isn't the view then declined? Well, for sure it is.
Yes, that's an excellent question. So there are different ways to look at this. A lot of our customers have active lighting on their vehicles, which allows for enough light to do the work we need to do. The same with passive lighting from street lamps and all this. So in most urban settings, we've not seen an issue with this. It of course will depend on the customer, but this is something we look at on a customer to customer basis, because so far most of our customers, we've not seen any issues in that respect. When it comes to rain and snow, so in light rain and snow conditions, this is typically not an issue. We haven't looked really at covering stronger rain and snow conditions as of yet, because most of our customers do not plan to deploy autonomous systems in such dangerous and challenging environments for the time being.
Yeah, and in addition to that, I saw also you have been testing it, going into a dark parking lot with low light conditions, and still the results are really tremendous, I think. So, but yeah, this is also something to test out in your specific environment. We will do some snow testing soon also with heavy snow, either falling down or on the side of the roads where everything is white. These are all conditions that we are now testing the system for also. And fixed position is continuously improving these harsh conditions. From Ferry, the question, how much does the XVN rely on the GNSS system reporting correct covariances or error bounds? Or is it able to detect wrongly GNSS solutions and ignore them because of the inertial and the vision system?
So that's an excellent question, and we do rely on them to a certain degree, but we are able to detect wrong GNSS solutions and ignore them thanks to our VIO. This is where our optimization approach really plays a big difference, because it's really advanced. It's able to retroactively correct wrong assumptions to ensure maximum accuracy in real time, but also by having so many parameters, by taking in a lot of raw data, by having two GNSS raw data receivers as well as the other sensors, we are able to do a lot of checks, balances, and optimize to minimize the total error with a priori estimations, because our optimization is a closed loop function where we estimate where we are, we take the measurements, we compare that with what we're measuring from the different sensors, and we optimize it all together. So if we receive data that really doesn't make sense, and the dynamics, for example, that would have pulled us away suddenly 5 meters, even though it has a very low covariance, don't agree with the other sensors, we're able to detect that and ignore it.
Okay, and is it also possible to use GNSS data from different manufacturers, or only the embedded GNSS receiver as currently is in the XVN?
So currently the XVN uses the embedded ones, of course, but our algorithms and the X-Fusion software is able to use receivers from different manufacturers, and that is also something we look at with different customers who are building different applications where they might use the X-Fusion engine.
Okay. And then a question from Haoming. How is the problem of drift in attitude or altitude? In altitude handled? Is it based on altitude information from GNSS or incorporating sensors like barometers, or is it based on the assumption that the setup is just running on the ground? So the third dimension, altitude.
That's also a really good question and very interesting, because we do have some customers that want to deploy our technology on drones, but currently we focus on ground robotics. However, 3D positioning is important for ground robotics as well. We see it in particular with our agriculture and lawnmower customers, where they have to move through terrains that might have hills, that might be slanted. So our truth, like for everything, starts off with the GNSS, and then we estimate the change in altitude based on our VIO. We do have a barometer inside. Currently, we don't rely on it too much. Currently, we're more focused on relying on the VIO to estimate how our altitude changes, and and we optimize this over the whole problem. We get our 3D position that is accurate to maybe 4 to 5 centimeters, which is usually enough for most of our customers. And more importantly, because we have a dual GNSS receiver system and we have 2 antennas, we're able to really accurately get not just the altitude, but also the orientation. So you get your pitch, your roll, to also estimate how the vehicle might be positioned on a slope.
Okay then. Thank you for that. Klaus is asking, your system also use wheel odometry for localization. So how well can you deal with slippage of the wheels? Is that a problem or not?
Yeah, so this goes back to the answer I gave earlier. There was a question about us ignoring bad GNSS measurements with a good covariance. So it's sort of similar. Because we have so many measurements, because of the way our optimizer works in this closed loop multi-open state system, we're able to identify measurements that just don't make sense with what we're estimating now, and we're able to reduce the weight of the impact of that measurement over the whole estimation problem.
Okay then. And Daniel, what data is available to the user? Are the camera images, for example, or other raw image, these also still available to the user?
Yes, so the XSense outputs a custom message that includes a lot of information from covariances, the state of GNSS, your position, your orientation, the relevant covariance for each of those. But in addition to that, we do have the ability to share with you the raw camera stream, to share with you the raw GNSS data, to share with you the raw IMU data. So all of that is also available to you.
Yeah. And all real time, right? So,
all in real time, yes.
Yeah. Then Philip, how well does the VIO work in an open field where there are not many detectable features or objects?
Yeah, another good question. I mean, that is always a challenge. From most of our use cases so far, we see that it can handle it generally quite well, especially if we have wheel speed added in there. But overall, we find that in most cases in open field, that's where GNSS takes over and does the bulk of the work.
Yeah. Yeah, that would also be my idea. That's the interesting part of this solution. If you have bad GNSS conditions, it means there's something nearby that blocks this GNSS, and that's something nearby you can use to determine your speed and your new position, right? That's exactly the technology we're offering here. Okay. How much of time will XVN continue to estimate position after it has lost the signal of GNSS RTK?
Another good question. So actually, our position estimation is not based on time, but rather on distance traveled. So it will be able to continue to estimate your position indefinitely. But as mentioned earlier, the GNSS RTK, you have a map, it's a global position. But as soon as we lose it, we're talking here about relative positioning. So we're only estimating how our position and orientation change. So it really depends what distance you're traveling in that outage rather than time, because we don't have that time-dependent drift. But we see in a platform where the sensor is well adapted, correctly integrated, we typically experience about 0.5% drift over distance traveled.
And but the position will be out. The estimation of the position will continue to be outputted for indefinitely, basically. But of course, yeah, the drift will get bigger and bigger.
Exactly.
Yeah. So then the last question, I think we can do 3 minutes to go, from Jules. XCM performances are impressive on your test cases. Will you also try and LiDAR and add LiDAR to tackle worse test cases, like, for example, the ones mentioned with the bad light conditions?
That's something we're exploring, and we've had a number of LiDAR manufacturers contact us to show interest.
Mm-hmm.
At the moment, it's not a focus because we've not run into the situations yet where this is imperative. But as we develop, and if it's necessary to tackle specific use cases, this is something our Fusion engine can already handle, because it's just another external sensor to add in. So it would just be about handling the LiDAR data and measurements to add it into the Fusion engine.
Okay. Thank you very much for that, Peter. I think we have answered all the questions that came up. And yeah, thank you again for this presentation. Like I say, I consider this really as the holy grail of positioning. Doesn't matter where you go, if you know it, if you don't know the environment in advance, or it has changed completely, it doesn't matter. You can still determine real time, smooth your position. And that's exactly what a robotic vehicle needs. They can't deal with exceptions and with all kind of position jumps. So yeah, very nice solution. So Peter, thank you very much.
Thank you, Minded. And yeah, if anyone's interested to actually experience this, reach out to the technical support team at Movella, and they will gladly show you. Yeah. Thank you, everyone.
Thank you. Bye-bye. Speak to you later. And then we slowly move on to our last speaker. So we're from Zurich in the mountains, and where it's probably also quite cold now. We move to Eindhoven in the Netherlands, where a very small, interesting company is located with very smart and very practical engineers. And they are now represented by Ferry Schoenmakers. Ferry, I would say the floor is yours.
Yeah, thank you, Meijnerd, for the introduction. So indeed here in Eindhoven, outside it's rather cold, but luckily in the office it's nicely warm. All right, so welcome to my talk about Nobleo technology. So I will present our company to you, but especially highlight the developments we did in auto robotics, and of course the challenges that go with the auto localization and navigation in these applications. First, I'd like to start with introducing the company, and it's of course best done with our new brand movie, which can also be viewed on YouTube, so then the audio is included. So Nobleo started in 2011 as a consultancy company in the high-tech domain. And since 2017, we are also a projects company, which means that we also do projects in-house for customers in the high-tech domain. So we do all kinds of technical projects, which I will come back to later, with a lot of expertise combined, with a lot of mixed teams working on these projects to get to all kinds of solutions. So we have a big focus on a good team, which means that we can make nice solutions, but of course we also focus on nice activities. So already some of our solutions are here in the video, which we will come back to in a few slides. And also some of our expertises are highlighted here. And this is, of course, the part where it is also interesting. So we also put a good focus on team effort and celebrating together. So where are we situated? We are in Eindhoven. We are now living in the Petrakerk, which is a former church, which is now being rebuilt as the Nobleo office, fully inhabited now with Nobleo people. And actually, this building is already getting a bit small. So we're looking already for other housing because Nobleo is growing. We're also neatly situated in Eindhoven near the high-tech campus, near big companies like Philips, NXP, ASML, but also rather close to the University of Technology in Eindhoven. So we also have a nice link with new technologies and new students. So basically, if you look at Noblet Technology, we have three big pillars in our company: autonomous intelligent systems. So autonomous will be the part where I'm talking about today, which is a domain where we develop all type of robotic autonomous applications, basically to relieve us of dirty, dull, and dangerous jobs. Then we also have an intelligence sector, and here we develop all type of like vision applications, AI applications, neural networks to help customers with those kind of problems or issues. And we also have the systems pillar, where we focus on the high-tech mechatronics domain. So we have a lot of CAD engineers, dynamics and control people who are working on very high accurate systems for example, those big companies in the region of Eindhoven. And then underneath, we also have the embedded part of Nobleo, which is basically a big team which is supporting us with embedded control platforms, software, drivers, or even electronics design to support our three major areas. So we're a consultancy company by origin, but nowadays we also do projects. We have a lot of mixed expertises in-house. So we do very well on system architecture and system design, but we also have a lot of people working in the software, electronics, and mechanics domain. And that's why we can support all these types of different projects. So then we get to the autonomy part. And if you focus on the autonomy pillar, we can basically depict the following timeline with the robotic applications that were more or less developed by now. So 6 years ago, we started with what we called Anna and Betty, which were just software platforms developed in-house to get some expertise, some knowledge, and some testing. And then Clara was actually the first real robot that we built for in-house testing. So Clara was the aim of a logistics robot for indoor logistic solutions. And with the expertise we got from Anna, Betty, but also Clara, we basically built our autonomy core box, which is depicted on the bottom left. So basically we had a box with a custom PCB inside, a computer stacked to this PCB, and our software stack. And with this box, we will be able to more easily get robots up and running. So the first one to prove that was Dory. So Dory you see there on the bottom left. And Dory is a boat. It's also actually the waste shark of the company Marine, for which we cooperated with them. And this is an aqua drone, which is the task is to collect floating debris in water and canals. So for example, plastic bottles and plastic bags. And this was a nice project where all the expertise of building a boat and all the marine technology came from Marine. And we were assisting them with picking the correct hardware and software to make this a robot, basically. So then Emma is the next in line. This is an existing so-called magnetic crawler, which means that it is basically a car driving around with a joystick remotely controlled with very big, heavy magnets on the bottom, which makes it possible for this vehicle to drive vertically on a steel wall. And this was actually a fun project where we basically took our robotics box, we put it on this existing carriage, and then created a robot from this platform. So then we had some expertise with also magnetic crawlers, and we created Fedra. And Fedra was a cooperation where we basically made a laminating machine, which is also a magnetic crawler that can drive vertically. And the task of this machine is to put foil to the bottom, or actually to the side of the wall where it is driving on. And this was an investigational project, for example, for ship vessels, where after it gets to the dry dock, it gets stripped of all the old paint on the ship. And then a foil is stick to this vessel instead of a new coat of paint to have a more endurance coating on the ship. Then we got to Glory. Glory is basically a project where we combined a robotic arm from Smart Robotics with our Clara platform to create an even smarter indoor logistics application. Then we go to Harvey, which we will also highlight further on. Harvey is an agricultural robot where the machine is built by the company Exceed, also a Dutch company, and we are developing the autonomy software for this machine. Ida is a pallet truck, which is one of these projects where we basically take an existing machine out of the market, we stuck our Nubleo autonomy core inside, and we created a robot from this application. And JAX is another one where we have a proof point of a sweeper. So JAX is the indoor sweeper, where we also take an existing machine from the domain, which is already steered by wire. So we then install our Nubleo autonomy core box, and we try to make this machine autonomous. Kirby then is a magnetic crawler with a mapping application. So basically a robot with a lot of sensors and 3D lidars to make 3D maps of the environment it's driving in. And Link is another platform based on this same magnetic crawler, where we stuck a robotic arm to this crawler. And this robot is then for remote operation, remote inspection, and remote maintenance, for example, in the oil and gas sector that people cannot or don't want to be. And finally, in this timeline, Molly. Molly is also a sweeper robot, but this is a outdoor sweeper robot. This robot is not autonomously driving yet, but mostly has to do with rules and regulations. But on this robot, it's very interesting to automate the task of the brushes and the spraying of this machine, so that the operator can focus on the driving, and we will do the rest for him. So that's quite a timeline. And because we're focusing on the outdoor robotics part, then these robots basically are all outdoor related. So I will now highlight some of them and the challenges that we got there. So to start with Dory, which is depicted here a bit bigger. So as told, the company Remarine came to us to help them assist with the technology part of this aqua drone, which is called WasteShark. And one of the first challenges, of course, here is cost. To have a feasible business case for this robot, the platform should be quite low cost, such that people actually want to buy it and deploy them. And it would, of course, be even better if we can deploy fleets, so multiple of these robots. The drone is actually driven with 3 thrusters, and of course it's a boat, so if there's some current in the water, it can drift a little bit to the side. So it's very hard to get any useful information from these thrusters for our localization. So if you have a wheeled robot, you can use the wheel odometry to include in your localization algorithm. The thruster commands here are hardly usable actually. The localization required for this robot is not that high accurate because we don't really need the centimeter accuracy here, but of course we do want to know where this robot is. Thus here we chose for a combination of a GPS, an IMU, and an electronic compass, because it's also worth to note in what direction you are looking. And a good thing about this aqua drone is that you're not so often big to metal structures, so an electronic compass is often sufficient enough to localize this aqua drone in the place that you want to be. There was one extra application which was developed later on, and it was an autonomous docking solution. So basically on the shore there is an autonomous dock which every now and then grabs the WasteShark, pulls it out of the water. It can charge the batteries, but it can also empty the basket of all the waste that it collected. And for this specific application we do need high accuracy because of course we need to accurately dock into the station. So for this solution we did implement RTK GPS. And in this specific application, we made the actual docking station the RTK base station, so that we are very accurate with respect to this base station. And we also implemented visual servering, where with a cheap camera, we can also look to some markers on this base station to make it easier to dock this machine. So here a little movie from Remarine to show what this WasteShark is actually doing. You can see that on the top of this WasteShark there's also a LiDAR installed. But mostly if you're on the water, there's not that much features to map. So this LiDAR is mainly installed for anti-collision purposes, so that if we come close to other boats or vessels, that we don't collide with them. So that's the Dory application, and throughout this application, all the other applications, you will see that often we combine, as many people do, of course, a set of sensors for the localization. And we fuse these different sensors together to get the best position estimate with this sensor set. And of course, a famous way to do it is with a well-known Kalman filter, which the previous speakers already mentioned as well. So that is a possibility to fuse multiple sensor inputs together Also, sensors with different rates can be combined, and sensors with different precision or accuracy can be combined. Of course, it's not an invention of Nubleo, it's mainly our expertise. And the biggest expertise here is, of course, the knowledge of how to neatly fuse these sensors, how to pick the correct gain matrices to make this fusion go the way that you want to. So I won't go into big detail about this gamma filter concept. If you want to know some more, we did a publication in the Dutch Micronique magazine, the 5th issue of 2020, on which we tell a little bit more about this concept. So then the next application is basically the range of magnetic quarlers, which in the timeline were called Emma, the Beetle, and Phaedra. Most of these quarlers are industrial cleaning applications. So for example, in the oil and gas industry, where you have a very big oil storage tank and you want to clean it or you want to strip the outside from paint. But you can also do inspection, for example. So for these platforms, we basically need 2D, 2.5D localization because you're always attached to a wall. So in that direction, it's not so interesting to know where you are. You want to know where you are with respect to this wall. So the accuracy is limited, but there is a certain degree that is needed. So nowadays, these cars are steered by a remote control and an operator observing them. So yeah, our eye is also not centimeter or millimeter accurate, but in the range of 10 centimeters should definitely be possible. Cost and robustness here are also important factors, especially the robustness parts, because for this industrial application, there's a lot of, for example, high pressure washers involved, a lot of heavy stuff involved. So you really want to have it very robust so that things don't get destroyed. Since this is a wheeled vehicle, we can also use the wheel odometry for the localization. But since we're driving vertically on steel walls, slip is very common. So we really need to take that into account. So our localization solution here was a combination of using wheel encoders, again an inertial measurement unit, and then the 9DOF variant, which Meindert taught in the previous presentation. So basically with all the sensors included. But there's also other solutions which I will highlight a little bit later. Just to get an idea here, first a video of one of our first tests with this platform, where you can see one of the typical applications. Of course, this is a test wall. It's not the size that we usually do, but here you can see the robot driving certain vertical lanes. And there's like a high pressure water sprayer attached to clean this surface. And there's also a hose attached then to, again, suck back all the water and debris that comes from this. Just to highlight again how important this slippage is. Here we can see the same robot, and at this time the operator is driving the robot with the joystick. So the command for the robot is to go perfectly in a straight direction forward. But you can see that while driving, the robot is actually going down slightly because of the shear that is happening in the wheels because of all the big forces involved. So that's tricky because your wheel encoders will tell you you're going perfectly forward, but in reality you're actually going downward. So what now happens is if you then switch on our autonomy software, it will notice this, it will compensate for that, and then basically you end up with a robot which is slightly angled, but by being angled you compensate for the shear of the wheels, and you are in fact driving perfectly straight. So if you compare now, for example, the black handle of this robot with the weld line that you can see on the steel plate, you will see that we're actually exactly tracking this, so that we can now perfectly compensate for the shear in the wheels. Here's another video, and here you can see that we also attached a LiDAR system to this robot. And with this LiDAR, you will also have more information about where you are. So especially the ground is very well visible. So for a height estimation, this is a very good sensor. And with the 360-degree LiDAR, it also does not really matter in which orientation the robot is. And also if there are other features, for example, on the ground, which you can see in the left bottom, we can also take these features into account. And you can also use the LiDAR system for an estimation of your horizontal position. So here you can see the overlay of the video of the robot driving around and the data of the LiDAR system, but also the path planning that it tries to do. So in this case, we're trying to follow horizontal lines, and then we painted the parts that we already went to. And one final solution I wanted to highlight, we also tested with what would be a local solution to have absolute localization on the system. And an idea could be to use a camera system and so-called AR markers. So you stick some of the markers to the wall and one or more markers to the robot, and then you can reference those markers to each other. So this requires, of course, an external system with an external camera. But once you have this system set up, you have a very high precision localization system, which is independent of the rest of the surroundings. So if there's no big features nearby which the LiDAR can utilize, then you can, for example, fall back to this solution. You can also saw that the robot, again, while rotating, drifted downwards because of the weight. But with this system, of course, you can easily detect that and again compensate for it. These markers are then printed on magnetic paper, so it's very easy also to apply them. So that's for the magnetic crawlers. The last application I wanted to highlight is the autonomous tractor, which we call Harvey in the timeline. So this is an agricultural application, which you've already seen before as well. The machine is being built by the Dutch company Exceed. We have a lot of knowledge in the agricultural domain and the building of these machines. And Obleo is cooperating with this company to make the autonomy software on this robot. So for this application, we need a full 6-dimension localization as we depicted. So that means you want to know the position in latitude, longitude, but also the height. And next to that, you also want to know the orientation of the vehicle. So do we have any roll, pitch, or yaw involved as well? Because in the Netherlands or Germany, those fields can be very flat, but in other areas in the world, they might not be. And you might be on a very hilly field, and you also want to know and compensate for that. For this application, we also need high accuracy, which is between brackets, because you want to go to centimeter level accuracy, which is, of course, high accuracy for such a machine. Because you want to, if you go, for example, cultivating, as is depicting in the picture, you want to have neat lanes next to each other with minimum overlap. You don't want to have any soil that you didn't touch. And even more important, if later on there is crops on the field and you want to do some processing within these crops, for example, weeding, then you definitely want to be sure not to drive over these crops. So we need some high accuracy localization. Cost here is somewhat important, but these machines are rather expensive. So yeah, we can spend a little bit more here on high precision sensors. The Aqua drone was really cost driven, so to say. The downside, of course, of a typical agricultural field is that there's just field, so there's less features around for mapping for a LiDAR application. So the LiDAR on this machine is used for anti-collision purposes and it can hardly be used for the localization benefits. Also, it is not really desired that we need extra equipment here to have this robot driving around. So you could decide, for example, to install some extra RTK base stations, or you could even come up maybe with this camera and marker solution, but it's not desired to have this on the fields, especially not if the fields are getting very, very big. So for the localization solution here, we ended up with using the wheel encoders, or more accurately, the tracks in this case. We have a dual inertial measurement system on this system, as well as a dual RTK GNSS system. And with using a dual GNSS system, it's also possible to get your heading information from the satellite system, which means that we're not influenced by metal structures around, but also the big metal chunk of the robot itself and the high voltage system that is installed to the robot, which make it very hard for an electronic compass to function well. And the last thing you want to do is to drive skew lanes with this robot. You want to have very straight lanes, of course. So to just give you an idea, this is a snippet from one of the videos from Exceed, but if you go to their YouTube channel, you can see way more of the applications and the videos that they've done, and you can see the robots driving around. In principle, they now have 3 different systems. So one is the tracked version, this is the 4-wheel version, all for tillage and field work, and they also have this small tricycle, which is there for orchards, for example, for a spraying application. Before I go here, it's also nice to note that with this robot, we also tested the XPN system, which was presented in the previous presentation, because one of the hard things, of course, is this use case where we drive in the orchards, but also if you drive on a typical agricultural field, and you're driving near the sides of it, where there is big tree lines and trees get occluded, then it might also be harder for the GNSS system to have accurate localization. So we only have the preliminary results, but we're also testing with this Vision Navigator to see if this is a nice system to use on these robots. So as told, the navigation part here is just as important as the localization part, especially if you're driving lines on a field where you do work. You definitely want to have neat and straight lines. And the last thing a farmer wants is that his field is all skew and slurry, and the neighbor looks to it like, what did you for a shitty job? So you really want to have a good performance and straight lines. So for this application, we further developed our path tracking PID controller, is how we call it. So the plan of this robot is pre-planned, and the most important part is what they call the AB lines, so the straight lines, and we want to accurately track them. So if you did some control studies, then one of the ways to do it is using a PID controller. So this idea we also implemented here. So if you look to the top right picture, you can see the gray line, which is basically the path that we want to follow with the robot. Then you see the robot itself with a point between the wheels, which we call the base link, and you want this point to track the path as accurately as possible. So what we then do is we create a control point, which is basically a point projected into the front of the robot, and we then calculate the error between this control point and the projected goal point. And this is basically the point on the path, but then also projected forward with the same distance. So the distance between the control point and the projected goal point, that's basically the error that we control on. And on this error, you can deploy your PID controller. So the benefits here are twofold. So in one way, you are penalizing both a lateral offset as well as an angular offset to your path. So you control both with the PID controller. And next to that, the length that you use for projecting this control and goal points is basically another tuning variable for your controller, which more or less tunes the aggressiveness of your controller. Because the paths are pre-planned, we can also use feed forward, of course, which is mostly important if you make curves to make them very accurate. And also something that we call an MPC feature, which stands for Model Predictive Control. So that's depicted on the bottom left. So let's say we have a path that we want to track, and we're going to drive this, but we have too much speed. And this MPC can already predict that with this much speed, we're not going to make the corner, and we will go without the arrow bounds that are set. So the arrow bounds are here depicted with red lines. So if the MPC feature sees it, then we can live decelerate the robot to have a lower velocity such that we know that our tracking will be within the arrow bounds. So yeah, that's some highlights about the navigation of this system. Again, we presented this in the same Micronic article, issue 5 of 2020. So if you even want to know more about this, you can look it up. So this is a view of one of the fields. So as we said, the fields are pre-planned. So Exceed is a partner who developed a complete web portal for this. So it's basically 3 clicks of the mouse and the whole plan is generated. But you have the ability to see beforehand exactly what the robot is going to do, what your field will look like after it is finished. And you can also see if it's making some turns where you don't want it, and you can adjust the path before executing it. So on the right, you can see a zoomed in piece of this recipe, as we call it, where you can see that the AB lines are connected with just so-called bulb turns, or sometimes just straight turns, to make nice turns, to not disturb the field too much, and to connect all these lines together. And then if you execute this plan, you get a result like you can see here in the drone shots. And that was basically what I wanted to tell so far.
Okay, excellent. Thank you very much, Ferry. A lot of information, very in-depth, very open. Thank you very for that, showing really your expertise in the field. And also nice to see that people joining this conference thought about ground mobile robots. It's not only about ground, it's also at sea and also even climbing walls. So that's really spectacular what you guys are doing. It's really 3D stuff. I have one question here from Jan. For the Harvey robot, why do you use the dual IMUs?
Yeah, that's a good question. So in principle, it's not necessary because you can have enough information with a single IMU. In this case, it's mainly for redundancy purposes. We have seen some interesting situations where some IMUs sometimes get a bit confused, and that mainly seems to be causing by the vibrations from the diesel engine on board. So for redundancies, we have two systems mounted in a different location, such that we can ignore these strange scenarios.
Okay, thank you. And Teresa is asking, do you use AutoWare for the localization and navigation of any of your robots?
Yeah, that's a good question. So we don't use it in the deployed software, but we're definitely always looking with them in what they are developing, because they have a very big set of very nice software tools for the autonomous domain. But as the name implies, they're mainly focused at autonomous driving on the road. A lot of them also highly depend on LiDAR localization, which is a thing which is very hard to do for us on a field where there's no features at all. So there's definitely some aspects of their tools which are very interesting, but we don't use them in the deployed software.
Okay, then me myself, I have a last question, if I may, about the company Nubleo. So you have been developing now some very interesting autonomous solutions for basically Dutch companies. Are you only doing projects in the Netherlands, or are you also doing projects for other country enterprises in Europe or even globally? What is the, basically the scale of Nubleo to support companies out there that want to develop an autonomous vehicle?
Yeah, thank you. Also a good question. So no, there's basically no limit. Indeed, in the autonomous domain, most of the customers are either by origin Dutch, or at least the the bureau in the Netherlands is contacting us. But we also have some occasions where for testing, of course, we needed to go to America or somewhere else. And especially in our systems pillar, where we do the high-tech mechatronics part, we have a lot of customers overseas throughout the world. So no, we're definitely not limited to the Netherlands, but it's just, in the region of Eindhoven already, there's so much companies involved in robotics, so there's a lot of work coming from there.
Okay, great. Okay, thank you very much. If there's no further questions, I would like to thank not only Ferry for his last presentation, but all the other presenters. We saw very impressive stuff being developed out there. It's real innovation, and that's what we also like to support from Movella, as we would, even though we are a very small component in the whole system, we love to see these innovations flourishing. So thank you very much for presenters and also the audience for watching, taking the time to stay with us and asking very good questions, which gave extra insight in these solutions. So I would just like to leave you to thank you also my team over here that from our marketing and technical department that made this possible.